Whether it's that smartphone sitting right there in your pocket or a massive server farm running the global internet, computing is literally everywhere. So today we're bringing you a clear, top-level explanation of the fundamental architecture that makes all of these incredible machines actually function.
Here is our roadmap for this explainer. First, we'll cover the von Neumann architecture. Then we'll meet the core components, unpack the instruction cycle, explore the power of interrupts, and finally look at modern system interconnections. By the end of these 5 logical steps, you'll finally understand what is actually happening inside your everyday devices. Okay, let's dive into this. Part 1, the von Neumann architecture, shifting from hardware to software.
Picture the very first computers for a second. They were these massive room-sized calculators. If you had a new math problem to solve, you literally had to go in and rewire the room. So pose this question to yourself. How do you even reprogram a machine like that without physically rewiring the whole thing? This was a massive historical problem, and early engineers desperately needed a way to make these inflexible, hardwired machines adaptable.
Well, the solution they came up with was profound. On one hand, we have programming in hardware, where the program is literally the physical wiring. On the other hand, we have programming in software. Instead of rewiring, we construct general-purpose hardware that performs different functions based on control signals. Think of a hardwired computer like a toaster. It's customized to only do one thing, make toast. But programming in software? That's more like having a master chef in your kitchen. The chef is the general-purpose hardware. You just hand them a different recipe, which is your new set of instruction codes, and they can cook absolutely anything. This brilliant shift was spearheaded by John von Neumann over at the Institute for Advanced Studies, and he outlined what we now call the von Neumann architecture. It's based on 3 deceptively simple rules. First off, both data and the software instructions are stored together in a single read-write memory. Second, the contents of this memory are addressable by their specific location. And third, execution happens in a sequential fashion, basically stepping from one instruction to the very next. These 3 simple concepts, they are the foundational DNA for virtually all contemporary computer designs. All right, moving on to part 2, meet the core components, the actual anatomy of a computer.
So, zooming out to a top-level view, we've got the central processing unit, or CPU. And this brilliantly illustrates how the CPU exchanges data with the main memory and the input-output modules, all communicating across what we call the system bus. Now, inside the CPU itself are specialized registers, and these are absolutely crucial to understanding how the whole system operates.
First up is the program counter, or PC. Unless told otherwise, a computer executes sequentially. So think of the program counter as that little "you are here" dot on a map. It holds the specific memory address of the very next instruction to be fetched. It is quite literally how the computer always knows exactly where it is in a sequence of software instructions. Once the program counter points to that next instruction in memory, it gets fetched and loaded right here into the instruction register, or IR. This is where the processor actually interprets the code to figure out what action it needs to take, whether that's moving data around, doing some math, or controlling an external device. Next up, we have the memory address register, the MAR. Main memory is essentially this vast grid of locations. The MAR is the CPU's way of pointing a laser beam at one very specific location in that vast grid whenever it needs to read or write data. And finally, working hand in hand with the MAR is the memory buffer register, or MBR. If the MAR points to the location, the MBR is the actual holding area. Think of it like a bucket for the data itself as it travels back and forth between the CPU and memory.
Okay, let's zoom in even further. Part 3, the instruction cycle, the heartbeat of the processor.
So the crucial point here is that no matter how incredibly complex a program seems on the surface, it ultimately boils down to a repetitive 2-step heartbeat. Step 1, fetch the instruction. Step 2, execute the instruction. The flow is just relentless. Using that program counter we just talked about, the processor fetches the instruction. Then it immediately moves into the execute cycle to perform the action. And then it loops right back around. Fetch, execute, over and over until the program finally halts. I want to emphasize a quote directly from our source text here. Program execution consists of repeating the process of instruction fetch and instruction execution. It's almost hard to believe for sure, but this simple, relentless cycle is the true magic engine behind every single software application running on your devices right now. But we do have to introduce a real-world complication. Part 4, the power of interrupts, breaking the sequential rules.
Imagine you're printing a massive document. Your processor is executing billions of cycles a second, right? But a physical printer is mechanically, agonizingly slow. If the CPU had to just sit there and wait for the printer to finish its job, it would waste millions of cycles doing absolutely nothing. We desperately need a workaround for this.
Now, what's really interesting is the stark difference in efficiency when we compare the two methods. Without interrupts, the processor commands the printer to write, and the entire system just pauses. It is a massive bottleneck. But with interrupts, the processor issues the command and instantly goes back to running the user program concurrently. When the printer is finally ready, it essentially taps the processor on the shoulder with an interrupt request signal. The processor handles it and then resumes its work without missing a beat.
Bringing us to our final structural piece. Part 5, Modern System Interconnections. How the components talk today.
Modern demands for power mean we've largely shifted away from those shared system buses to point-to-point interconnects, like Intel's QPI. Instead of a shared bus where components wait their turn, basically relying on centralized arbitration like a traffic cop, we now have multiple direct connections. It is fascinating because these internal connections operate incredibly similarly to the global internet. Data isn't just a raw stream anymore. It's broken down into tiny packets, zooming around a microscopic layered network right inside your CPU.
So we started with a room-sized machine requiring physical rewiring, and we've ended up with a microscopic, packetized network executing billions of fetch and execute cycles every single second. It really makes you wonder, if all the incredibly complex software we rely on eventually reduces to just these simple fetches, executes, and interrupts, what invisible cycles are shaping the digital world around you right now? Thank you so much for joining me on this explainer. I hope you never look at your devices the exact same way again.